Not boring.
I'm going against my lab.
All right, let's get started now with section B. You can see up on the screen that we're now going to deal with section B, which deals with a horizontally fired projectile. This is the one like we were talking about last period where we drew the picture in our notes. What we're now going to do for the rest of this unit, there's only two more sections, B and C. Again, it's a fairly short unit. Is all about the problem solving. How do you actually solve problems with these? Not just answer conceptual questions. We just did the conceptual piece of the unit. We're now going to talk about the problem solving involved with the two different types of horizontal and vertical motion. And this first one focuses on a horizontally fired projectile, which is being illustrated for you in that animation on the screen. For example, a package being dropped out of an airplane. The airplane gives it a horizontal motion because the package is initially moving sideways with the plane, and then it gets dropped outward, which means it's moving out and down simultaneously. So this is what we call a horizontally fired projectile. And what I'll ask you to do on your quiz on Thursday on this topic is to use vectors, graphs, and equations to describe how these projectiles move and then solve problems involving these types of projectiles. Okay, there are no new equations in this unit. So it's all the math that we already know. We're just applying it to this type of motion. So let's just review what is meant by a horizontal projectile. A horizontal projectile is launched with some horizontal velocity from some elevated height or elevated position. And we end up getting a ticker tape that looks something like this. If I were to draw the motion diagram, the ticker tape, we end up seeing that parabola that we get when we combine the outward motion with the dropped motion. So as we're going to see with all of these projectiles in this unit that we're focusing on, we're going to end up seeing that parabolic shaped trajectory because in the outward direction, it's gravity free, and in the downward direction, we have the acceleration. Now, the kinds of things that I'll ask you to solve for could be any of these four things. Sometimes it's multiple things. I could ask you how fast it was moving initially. What is the initial speed of the projectile as it's launched? I could ask you, what's the height of the cliff that it's being launched off of, the initial height of our projectile? I could ask you to find the hang time, which is the time of flight. How long does it take it to go from the top of the cliff down to the ground? Or I could ask you to solve for the range, which is the horizontal distance from the launch position to the landing position. That is the range going outward in the forward direction. Is everybody all set with those notes? The way we solve these is different than what we've done previously. There's some extra steps. A lot of students go, oh my gosh, these questions are so long. Yes, they are long, and they will take you a little while to do one problem. But just because it's long doesn't mean it's hard. We're going to do enough of them that hopefully you begin to see a pattern in terms of what you need to do. So let's talk about what we should understand about these projectiles. Remember that these types of projectiles are moving in two directions simultaneously, outward and vertically. Remember that the horizontal and vertical components of motion are independent of each other because the horizontal and vertical directions are perpendicular to each other. So they will not affect one another, which means that when we solve these problems, we're going to need two distinct and separate sets of equations. We apply the guess method to the x direction and we apply it to the y direction separately, and they do not mix. They have to be segregated in order to solve these problems correctly. And you'll see how we do that, how I help you set it up so that way it is not going to be a cumbersome task, hopefully. When we do these questions, there are always certain things that we will know, but will not be explicitly stated. You just know them. Just like when we were doing dropped objects or objects thrown straight up in the air, we knew certain things that were not stated to us explicitly. So let's review what these things are that we should know without having to be told that these are the givens in the question. Everybody all set? Okay, so let's talk about how these motions can be described and therefore what we know, what our givens are. So remember, in the horizontal direction, that's where we describe having a constant velocity. Whenever you have a constant velocity, that means there's no acceleration. So we will always know that the acceleration outward is 0 meters per second squared. Always. You're not going to be told that. You just need to know it. In the vertical direction, for this type of projectile, this is where we have a constant acceleration. To be more specific, these types of projectiles are speeding up as they fall in the downward direction, which means that since they are being dropped as they are fired outward, they will start off with an initial velocity in the y direction of 0 meters per second, and they will have an acceleration in the vertical or y direction equal to negative 9.81 meter per second squared, so long as the problem takes place on Earth. If we all of a sudden do the problem on Mars or on the moon, we don't use negative 9.81. Remember, that number is dependent on the planetary object that you're on. Okay, so let's go through some steps or hints so that way you can solve these problems correctly. The first thing I am going to ask you to do for every question is to make a sketch of the situation. So step one, before we do our guess stuff, is always going to be to make a sketch of the situation. And I will model this for you in our first problem together. The sketches all look the same for this type of projectile. Then you're going to go ahead and list your givens. But notice that the givens are now going to go into a table format. And we're going to put what we know about the horizontal direction in one column of the table and what we know about the vertical direction of motion in the other column of our table. This allows us to keep the two directions of motion separate from one another. They have to be segregated because the description of motion is not the same going out as it is coming down. Then you'll identify your unknown in the table. Everything is done, the first two steps of our guess method, the G and the U, are done in the table. Identify the unknown in your table. So first step will be sketch it. Second will be list the givens in a table. Third step, identify your unknown in the table. Okay. Now, no matter what the question asks you to solve for, you always have to find the time in the air first. I don't care what the question asks for, you need the time first. And you'll use one of the two directions of motion, either the horizontal path or the dropped path, to find the time. You cannot use them together. You use one or the other. Which one you use to determine the time will be based upon which direction of motion you know more about. Wherever you know more, either in the X or Y direction, will determine which direction you're going to use to solve for the time. And then once you have the time, you will then find what you're looking for with the other direction of motion. So now that you know the time, you can use the other direction, the other set of givens, to solve for whatever you were asked for. And that is going to bring us to page 14 in our packet. So let's go there. Make sure you keep out your notes so you can look things up, but turn to page 14. You will need your reference tables and your calculators. What I want to do is walk you through how you set up and solve one of these questions. And that's what we're going to do for the rest of today and one period on Wednesday, is work through solving this type of projectile question. All right, so here we are on page 14, which at the top says Unit 5B, horizontally fired projectiles. These are the practice questions. I'm going to do number one for you. Number one states that we have an airplane traveling at 100 meters per second, and it drops a package from a height of 3.00 times 10 to the 3 meters. First thing I'm asking you to find is the time it takes for the package to get to the ground. And then in part B, in order for the package to reach a specific target on the ground, how far in front of the target does the package need to be dropped? So notice I started the way I always do. I read the question, I do my circling and my underlining. You can see I did that as I read the question. Now we're going to go to listing or making our sketch of the problem. And every sketch we make will look like this. It's essentially going to look like the cliff problem, where we have something going sideways and coming down to the ground in a parabolic shaped trajectory. We then list the things we know from the question on this picture. This value is the speed of the airplane. The airplane flies parallel to the ground. So that is the initial velocity in the x direction. We are told that is 100 meters per second in the problem. That is the speed of the airplane. That's how fast the package is moving before it gets dropped out of the plane. It's going sideways at 100 meters per second. We are also given this value, which refers to the height of the cliff. Now, the package is not going to go up. It's only going to come down. This is our vertical displacement, which we call dy. D for displacement, y in the vertical direction. Its value is 3.00 times 10 to the 3 meters. Now, there are two other things we are going to identify on our picture. One arrow is this. That arrow along the ground from the cliff to the landing point is the range, which we call dx. And we also label this point where it's hitting the ground with time t. I don't know either of these things. These are what we're being asked to solve for in parts A and B of the problem. Now what I'm going to do is list my givens in a chart. There will be 3 columns in this chart. The middle column will be for things we know about the x direction, and the right-hand column will be for things we know about the y or vertical direction. The first thing we will always know in either direction is the acceleration. In the x direction, the acceleration is always 0 meters per second squared. You won't be told that. You just know it because that's the gravity-free path. We also know the acceleration in our y direction. That's the acceleration of gravity, which is negative 9.81 meter per second squared. The next row will be for the initial velocity in the x and y direction. In this problem, I know the VI in the x direction. That was given to me, 100 meters per second. For this type of projectile, I also always know VI in the y direction. It's dropped. That means VI in the y direction is always 0 meters per second. Now, the next row will be for any displacements that we know. Right now, I do not know D in the x direction. That is a question mark. I do not know it. That's an unknown. Do I know D in the y direction? Yes, it's right here. Notice it points downward, which means it is negative. It's going to go down 3.00 times 10 to the 3 meters. The last variable we put in our chart is the time, t. And it turns out I don't know the time. So that is a question mark. But what's really cool about time is that the time to go out is the same as the time for it to come down. The time out and the time down are always equal to each other. They are always the same. So once you find it in one direction, you know it in the other. So let's now go to part A. Part A says find the time. Now we need to look at the chart to figure out which set of givens I know more about. Do I know more in the X direction or the Y direction? The Y, which means I am only going to use the Y set of givens to help me get the time. In other words, we completely block out the X column to solve this question. We ignore it. Pretend it's not there. I want the variable t. I have an A, a VI, and a D. So when I go to my reference table and I look at the equations I know, the only equation that has the A, the VI, the D, and the T I'm looking for is this one. D is VIT plus half AT squared. So that is the equation I'm going to write. I now need to solve it for T. But since T is in both terms on the right side of the equal sign, I need to simplify this first. Since I'm using the Y direction and the VI in that direction is 0, this part drops out, leaving me with D is 1/2 AT squared. So the time is the square root of 2D over A. What I substitute in are things I know about the Y direction, not the X, just the Y in this case. So let's substitute in. T is the square root of 2 times negative 3.00 times 10 to the 3 meters divided by negative 9.81 meter per second squared. We then go ahead and we solve it for the time, paying attention to units and sig figs. So I'm going to work that out on my calculator right now. And that gives me an answer with 3 sig figs based on the givens of 24.7 seconds. That is how long it takes this package to get down to the ground. This time now can go in my chart. I just found it here as 24.7 seconds, which means it's also 24.7 seconds in the X column. Now I go ahead to part B. Part B is asking me for how far in front of the target. Well, the target is here. That means I'm now asking you for the horizontal distance. I'm asking you to find D in the X direction. Since I'm looking for something in the X direction, I have to block out what I know about the Y direction. I can't use the Y stuff. I'm looking for something in the X. So if I know A, VI, I'm looking for D, and I have T, I can use the same equation I just had. But in this direction, what drops out? Look at your givens in the X direction. What's going to drop out, Ryder? So 1/2 AT squared will drop out because the A in the X is 0. This goes away, which means that the equation we will use simplifies to just D is VIT for the X direction. I can now go ahead and do my substitution with units. So D in the X direction will be 100 meters per second, which is the initial velocity in the X direction, times the time we just found, 24.7 seconds. We now go ahead and solve that, getting an answer with the appropriate 3 significant figures. And that gives me an answer of 2,470 meters. And that would be the answer that goes there, 2,470 meters in the D and the X column. Notice that when I'm done, my entire table is filled out. Any questions about how that's done? Takes a little bit longer than what we've done before, but it should be easily done if you remember to isolate the X and Y columns and not interchange them. Let's skip 2 for now. Let's go to number 3. Kiara, would you mind reading question 3 for us, please?
A pool ball leaves a 0.60 meter high table with an initial horizontal velocity of 2.4 meters per second. Predict the time required for the pool ball to fall to the ground. Calculate the horizontal distance between the cable's edge and the ball's end.
Okay, notice that I already tackled the circling and the underlining. So that means the next thing we're going to do is sketch it. Every problem looks exactly the same for this type of projectile, where it goes out and down to the ground. And we label on it our VI in the X direction, the D in the Y direction, that arrow coming down. The arrow going sideways is D in the X direction, and we have a time of T. Miriam, I circled the 0.60 meters. What value is that in this picture? That is the dy. Very good. 0.60 meters. So let's label that. Sydney, what is this 2.4 meters per second? That's the VIX, which means that the dx and the t are probably what I'm asking you for in this multi-step question. We can now go to our givens chart, which has 3 columns. The variables in the left and the X and Y are our column labels for the middle and right column. The first variable that we will list is always A. Vincent, what is A in the X direction always? 0 meters per second squared. Very good. Gianna, what is A in the Y direction always? Very good. The next variable we list is the VI. Ryan, what is VI in the X direction? That is correct. That was given in this problem, 2.4 meters per second. Jacob, what is it in the Y direction always? Yep, 0 meters per second, because in the vertical direction, it is just dropped. The next variable we have is D, the displacement. Alex, do I know D in the X direction? No, so that is a question mark. We're going to look for that. Nikolai, what is D in the Y direction? And what direction is that displacement? So I need to do what to this number? That's right. Without the negative sign, you will not get a calculator answer. The last variable we put in the chart is T. Devin, do I know what T is? Nope. So these are question marks. Let's go to part A. What am I asking you to find, Juan, in part A of this problem? Juan, what am I asking you to find in part A of this question? That's right. Now, Chaudhry, look at our 2 sets of givens. In which column do I know more? Which column, X or Y, do I know more?
Why?
The Y. So we will use the Y direction to help us get the time. All right, so let's see if we can locate an equation now, because these are my givens and my unknowns. I did the G and the U step in the table. Now I go to my E step, the equation. I have the A, the VI, and the D. I'm looking for T. Elisa, according to your reference table, what equation has those 4 variables? That's right. And since we're looking for T with this equation, we're going to have to simplify it before we can solve for T. Max, how does this simplify? What drops out? That's right, because the VI in the Y direction is 0. So this part of the equation will be 0, leaving us with D is 1/2 AT squared. And if we isolate the T, we get the square root of 2D over A. We can now go ahead and do our substitution with units. So T is the square root of 2 times negative 0.60 meters divided by negative 9.81 meter per second squared. And we just solve that for T now with appropriate units and sig figs. Khalees, do you have that time? Excellent. 0.35 seconds is correct. That time can now go up into your chart if you'd like. We found that here in the Y direction, but remember the time is the same in both directions, so I can list that in the X column now too. Let's now go to part B. Jackson, can you tell me what I'm looking for in part B? And in what direction is that distance? I'm sorry. That's the unit. In what direction? X or Y? Yeah, horizontal is the X direction. So we have to ignore the Y direction to solve this. Blake, I have an A, a VI, I'm looking for D, and I now know the T. What equation would work best with those variables? That is correct. We copy it off the reference table. Now, Emma, I can simplify this. In the X direction, what's 0? So what part of this is going to drop out? That's right. The 1/2 AT squared is going to become 0 because A in the X direction is 0, which means we're really just working with D is VIT when I use this in the X direction. Let's now go ahead and do our substitution with units. So D in the X direction would be 2.4 meters per second, which is the VI in the X, times the T we just calculated, 0.35 seconds. We're now going to solve that with 2 significant figures. Flavia, can you tell me what you get for that horizontal displacement? And the units, please? Meters, that's right. 0.84 meters is correct. And that, if we want, we can put back up in the chart, although it's not necessary. I like putting it back in the chart because that gives me that little bit of confirmation like, oh, yes, now I know everything. I know everything I needed to find. It's all there. Any questions on number 3? All right, let's go to number 4. Haley, would you mind reading number 4 for us, please? Very good. Okay, I did my circling and my underlining. So what's my next step, Gavin? Yep, make our sketch. And the sketch looks like that cliff. with something coming off the top of the cliff horizontally. We show the horizontal arrow at launch, label it VIX. We show the downward arrow on the left side of the cliff. That is your D and the Y. We show the parabola coming down to the ground, giving us a time T when it lands, and a horizontal range, which we label DX. Okay, Ryder, what is this 22.0 meters? That is the DY. That is right. Because it says that's the high, 22-meter high. So that's the height, the DY. Janicia, what is this 35.0 meters? Yes, that is the range, 35.0 meters. It means I don't know VIX or T. So let's now make our chart. What do we know about the directions in the X and the Y? Let's start with the variable A. Kiara, what is the acceleration always in the X direction? Yes, 0 meters per second squared. Miriam, what is the acceleration always in the Y direction? That's correct. The next row is for our VI values. Sydney, do I know what VI in the X direction is? Nope. Question mark. It's not labeled on my picture. I don't know it. Vincent, I should know the VI in the Y though, because that's not even on the picture. That's right. That is 0 meters per second because we're just dropping it. The next row is for the D. Gianna, do I know what D in the X direction is? What is it? I'm sorry, how much? 35.0. Yes, 35.0 meters. Ryan, what is D in the Y direction? And which way is it moving? Does it just get displaced up or down? So what does that down mean? It's got to be negative because it's always going down. Down is a negative direction. So when we write it in a table without the arrow, you have to put the sign. The last row is for the time T, which we do not know. Now, Jacob, what is this question asking you to find?
The horizontal velocity.
Yeah, so I'm asking you to find VI in the X direction. I'm going to tell you right now, you can't find it. If you remember in the notes, I told you always need to find something first, no matter what the question asks for. Alex, do you remember what you always have to get first? Look back at your notes if you don't remember. I think it was step 4. What do you always have to find first?
Direction.
No, not direction. Starts with a T, ends with an E. Time. You must find the time first. Because you can't get this without that. There's no way. Doesn't happen. Now, we tackle this just like we did before. You look at both columns. Nikolai, which one makes more sense to find the time?
Why?
Yeah, because you know more there. So we're going to use the Y direction to help us get the time. Even though we didn't ask for it, that's what you got to do. Otherwise, you can't get the answer you're looking for. Devin, what equation can we use to get the time? You got it. And I can simplify this because what's going to cancel out now, Juan?
VI.
Yep, the VIT is going to drop out. So D is 1/2 AT squared. That means the equation for T becomes the square root of 2D over A. So we do the square root of 2 times negative 22.0 meters over negative 9.81 meter per second squared to give us the time. So let's work that out. We need an answer with 3 sig figs for the time. Audrey, let me know when you have that time, please.
Wait. I know what I'm doing. Okay, 2 point.
No. Elisa, what'd you get? No. Max, what'd you get? Square root of 2 times 22 divided by 9.81. Okay, what'd you get? Sorry, 2 point. There you go. Yeah, my mistake. 2.12 seconds. Actually, I'm not boxing it in because that's not the final answer to the question. We'll finish this off on Wednesday. Have a great day, folks.
Oh, sorry. Okay.
There we go.
I was
My mistake. Yes, it does. Thanks. You too.